Hello, hello. Hey guys, I am Terence from Option Labs. I am a core developer. I mostly work on layer 1, like Ethereum layer 1. I don't spend too much time on layer 2. But here I am talking about layer 2 sequencing. I kind of went down this rabbit hole over the last few weeks just because I thought sequencing was very interesting and there was just like a bunch of like Twitter like threads on sequencing, blah, blah, blah. So yeah, just wanted to share what I have learned over the last few weeks. So yeah, hopefully it's informative and insightful. So agenda, right? I want to kind of like go over like at the very fundamental, at the very base layer, like why do we sequence? And then like I kind of want to talk about like the separation of concern, like between sequencing and execution. Then finally, I will dive deeper into sequencing, like what does a sequencer do, what does a sequencer cannot do, what are some design goals for like what we call decentralized sequencing, because that seems like a hot topic. And then I want to talk about some landscape, and finally MEV, because that's very interesting. So why do we sequence, right? I think like we need to understand that like for layer 2s, we don't need this sequencing like stuff. We can always use layer 1, right? So TX can be ordered from the parent chain. You can submit your Arbitrum optimism transaction to layer 1 Ethereum, and then they can be used, right? But we sequence because that's gonna be expensive. That's not economical. So sequencer does something really well, which that it aggregates all the user transactions off-chain, compress it, batch it, and commit it over a single transaction. So the win here is the compression. It minimizes users' cost, and then but there's some trade-off, right? Because now you have to batch everything together, you have to wait, and the time to finality becomes slightly longer. So I think we need to understand at the very least, right, there is some censorship resistance here because sequencer cannot censor your transaction because you can still submit them onto layer 1. But then, of course, there's like the UX and the user cost, which I will get more into. So sequence and execution. I have a diagram for the next slide, so bear with me, right? So there is this separation concern. You have your layer 2 sequencer, then you have your layer 2 proposer or validator, right? It's important to know that separation concern is, in my mind, it's a feature, it's not a bug. And then it's important to know that once the transaction is posted on layer 1, the parent chain, it is final, yeah? And then why separate? Because they are a separate entity, right? There is not a circular dependency, and then only the proposer, the validator, requires the sequence. So let's quickly look at this diagram. This is from like this is from an Arbitrum doc. You have your transactions, and then it goes to the sequencer, and then the sequencer will emit the soft feed, basically a sequencer feed, and then so you get self-confirmation there. So that is nice because like dApps can use that, users can use that, and users love that. You get like 50 milliseconds like confirmation, and then in parallel, the sequencer will batch and compress it, and then submit it to layer 1, and then finally on the right side. Right side of the picture, there's validators which run state transition function and then compute layer 2 blocks. And that's where the execution side happens. So on the left side, you have sequencing. On the right side, you have execution. So what is sequencer's main role, yes? So let's be very clear. The sequencer receives transactions from the user. It emits ordered and timestamp sequence of the user transaction. It does two commit. It does soft commit, which is very fast. And then it does a hard commit, which means it batches it, it compresses it, it sends it to the layer 1. And then therefore, once the layer 1 finalized, you know your transaction is finalized, right? And then proposer finally takes its time to basically submit layer 2 blocks using the sequence feed. So it's important to know that the sequencer can do or cannot do, right? So there's some misinformation out there that sequencer cannot change the result of your transaction, right? So sequencer can only order your transaction. That means the sequencer can extract MEV, sequencer can front run you, blah, blah, blah. But then sequencer also cannot censor you forever, yeah? And then sequencer, actually in a lot of designs that I've seen, sequencer also doesn't collect execution fee. That's up to the validator to does it, which reimburse sequencer after. And the sequencer doesn't even decide how much to charge you. That's based on the layer 2 chain. So protocol only trust sequencer does one thing, right? And that is just to order transactions. That's it. So sequencer design goals, right? So if today you guys were designing a sequencer, what would you guys like to see, right? This is some of my opinion, what the sequencer should achieve. It should achieve liveness. If your sequencer goes down, your chain does not go down. You should have more than one sequencer. And then you should minimize the following. You should minimize, for example, the TX latency. So meaning that when you submit a transaction, the transaction should get confirmed as fast as possible. Just like using a Web 2 app. And then you should minimize toxic MEV, so then there's no front running. Also, it depends of your MEV philosophy of your chain. Some chain may decide to auction off the right, but some chain may not. But ideally, if you don't want to do that, then you should avoid front running. And of course, you should reduce co-location incentive to make it like not a lot of back running happen, because we have seen that from a lot of layer 2 these days. There's lots of back running. Finally, we should have censorship resistance. So there's a lot of sequencing designs out there, right? Right now, today, all the sequences are centralized, and then there's lots of talks on partial and full centralized design, and finally, there's shared and outsourced design. So I'll go over them one by one. So it's important to note that in the outsourced design, it just means that your sequencer can be outsourced to another sequencer. For example, there's shared sequencing, there's layer 2 chain, for example, like Swap from Flashbots, also like layer 1 chain. So your sequencer can be outsourced to other things here as well. So let's break down the problem. So when I think of this problem, this is probably the most important slide of the whole deck. It's just like, I like to break down the problem into the following, right? Decentralized sequencer is really just a set of computers that implement some ordering policy through some consensus algorithm. So if you really break down the problem like this, the problem becomes probably much easier to solve. So let's talk about ordering policy. So these are the ordering policy that we have seen last. So we have first come, first serve, which is implemented in most of layer 2 today. We have MEVA, which was proposed a few years ago, which does full block auction. It auctions off the right of the sequencer row. And then there's time boost, which was proposed earlier this year, which allows some back running. And then there's two versions of that. There's continuous time and there's discrete time. So first come, first serve. Why first come, first serve, right? What are the pros and cons? It's easy to understand. It minimizes transaction latency. It minimizes toxic MEV, so it means that because it's first come, first serve, you trust the sequencer to not front you, then sequencer doesn't front run you. But then it doesn't resolve race by bidding, so that sucks, because now you have lots of back running happening in the back. Then there's MEV auction. So MEV auction was proposed a few years ago by Carr. Is that anyone can become a sequencer by bidding. So you essentially, if you want to be a sequencer, you bid your right to sequence a block at the future time. And then the highest, and then like in this model, right, it's important to know that the bid should be as close as the value extracted. So say today, if you can extract 100 ETH block, then you will bid up to 99.9999 ETH because you can still make profit, right? There's a few unknowns that I haven't quite figured out with MEV auction. Feel free to add me. It's that in terms of timing and censorship, in terms of just for that efficiency alone, that to me, that's a question mark. And there is time boost. So time boost was proposed earlier this year by Option Labs. So it basically auction off back running, so it allows the bidder, the users, to buy time. And then there is like this G boundary, meaning that you cannot buy more than like 500 milliseconds of time. So that means that if you're a user, your worst time is 500 milliseconds. So if you don't want to buy time, if you send a transaction, you only have to wait up to 500 milliseconds. So that's nice. And this result raised by bidding. So there's no front running if the sequencer is honest. And there's the two models of that, which I won't get more into. But yeah, we're analyzing which one's more efficient. So let's do a comparison, right? So we have this first come, first serve, MEV auction, time boost. So first come, first serve wins at the latency game, of course, because it's first come, first serve. There's not much to do with it. And then it reduced toxic MEV. But then if you look at it, right, it's like you always have to trust the sequencer not to reorder, because that's not a problem of ordering policy, which I will get more into. And then you have time boost, which kind of like solve a little bit everything, but you have to make a sacrifice on latency, because now if you don't want to use time boost, you don't want to buy time, you have to wait 500 milliseconds basically. And then there's MEV option, which is like, if you want to reduce toxic MEV, I'm not sure MEV option is the way to go, but it also does resolve race by bidding, and that is nice. So for sequencer consensus policy, right, there's like, how do you decide like who's a sequencer? There is a few consensus algorithm out there. You can use leader auction, you can use random leader auction, you can use economic competition, you can use threshold cryptography. So I want to start going over like what does it mean when you add consensus into the order policy, right? Just like I said, the order policy I mentioned earlier can be applied to any design. And then like as long as the committee reaches consensus by ordering, then we are good, right? So there is this safety assumption, and there's this trade-off between latency and size. So let's start with the first design, right? You just decentralize via committee. This is like the poor man version. Everything through social consensus. You have a DAO, and then DAO can vote who is the sequencer, and then the order policy is even voted through the protocol. And then front run could be can be detected out of band and slash, right? So then you have this reserved sequencer for liveness. And this also requires some, I mean, this is like decentralized, but it requires some manual intervention, because if someone goes bad, you need to do this manual intervention, and it's maybe slow, maybe not ideal. Then you have this BFT. So you apply BFT consensus on the sequencer side. This is another approach, yeah. And then so the only difference is here is just everything's gossip to the P2P network, and then you have very good liveness, but it's very slow. Because what we know, like gossiping through network is not fast. So, but with that, you have this advantage that manual intervention is not required. So there's another approach that add on to the previous one, you decentralize via committee, and you use some threshold encryption decryption. So in this approach, that is leaderless, anyone can batch post, and then the encrypt transaction goes to all the party, and party to work together to decrypt all the transactions, and then the party reaches consensus, and then this requires autonomic broadcast protocol, and then there's still non-trivial latency, but it is slightly better than just the committee itself. And then let's do some comparison here. So I mean, this is probably a lot to digest, sorry, but then like, as you can see, right, the committee just by itself has faster latency, it hits all the goals, but then the committee plus the threshold is probably better in terms of censorship resistance and then reduced co-location incentive. So last but not least, I want to touch base on shared sequencing, because that's been pretty hot topic lately, right? I think shared sequencing wins in two areas. The first area is that shared sequencing can achieve very efficient data packing, meaning that if you have your smaller blobs, you can essentially share blob of data spaces, and that's quite nice, right? Because for every blob, it's about 128 kilobytes in the 4844 world. And then smaller blob might take a long time to fill the space, but you have more blobs, you can fill the space faster. And then that's where shared sequencer comes in. And the shared sequencer also does cross-domain value extraction better than just a single sequencer. And that's a no-brainer. But then there's a few unknowns that like still wait to be resolved, right? Shared sequencer does automatic inclusion. It doesn't do execution, right? So then unless your shared sequencer runs every state transition function on every ROP, which may not scale, then how do you achieve that? Maybe there's a zero-knowledge solution out there, but yeah, so this space moves really fast, so maybe we'll see a solution to that. And finally, how do you distribute the value, the economic value back to the individual ROP, right? Suppose today you have a cross-domain MEV transaction that ROP A, B, and C or participate together, and then there is like 100 ETH being extracted, then how what number of ETH does A get, B get, and C get? So that is slightly unknownish. So I would love to see more research on that. So finally, my last slide, what is next? So I have no doubt the sequencer will be decentralized sooner than you think, and then an order policy will be adopted, right? And then it's also to know that like everything we do here is technical, but this is also will become political as well, right? Proposals will go through the DAO votes, and then like there may be multiple proposals, and the DAO itself will eventually decide which which ordering policy or which consensus to use, basically. So yeah, maybe there's a multiple winner, maybe there's one winner. That's something that we will see. So that's my last slide. So I will be here all day. I'm going to Arbitrum day after. I have a talk there, but I will be back after. So yeah, thank you guys. Enjoy the rest of your ECC.